Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to introduce Aaron Jansen today. Aaron is visiting us from Johns Hopkins University and the HLT Center of Excellence there. He got his PhD from the University of Chicago and has been pioneering a very interesting area of speech recognition involving making the detection of sparse events and then building models on top of those sparse events to do noise-robust speech recognition. And he's here today to describe this process. And additionally, somehow missed the memo that it's catastrophically dangerous to do live demos with speech recognizers. And he will actually attempt a live demo of this technology as well. So here he is.
Okay, thank you. Do I need to use this?
No,
during
you
some?
would just turn it off.
Okay.
Hold down button. Thanks.
Okay. Okay, thank you, Jeff, for the introduction and the invitation. So today I'm going to be telling you a bit about the work that I've been doing over the past 3 or 4 years, I guess now. Most of it was done while I was a graduate student as part of my PhD, and that was work done with my advisor, Partha Niyogi, who isn't the most central speech person, but he's a common name in machine learning communities. So the question behind this work essentially is that in mapping the speech signal to a sequence of words or phones or whatever it is the task you're interested in, is it actually optimal to break the speech signal up into frames, compute some short time representation, and then apply some sequential dynamic sequence model on top of that representation, or might it be better to sort of set up your sort of probabilistic shop at some other level of detail? And so in particular, what I've been proposing, and this is something that you probably got a good sense of from the title or what Jeff said, is that something much more sparse than frames could potentially be more optimal. What I'm going to try to argue today is that sparse, you can have a sparse representation that can still be sufficient to do good recognition and clean speech, but that when you actually sparsify, you might end up with a representation that's better in noisy speech. So to sort of give you a flavor of sort of why this might be a reasonable thing to do, first I have a simple example. So I'm going to play to you an audio clip of myself speaking a single word in isolation. And this is essentially the signal has been masked in a sort of principal way to 0. So you see in this case everything that's in black is what's left, everything that's in gray is what's been masked out. So I hope people understand that it says recognition, which you'd notice that in this case actually I've masked out 60% of the signal. You can still understand it. You can see in the spectrogram you have these sort of big blue patches where it's been masked out. And if you can imagine if you're going to sort of transform this into a set of state likelihoods, say for an HMM, you're going to have a hard time finding a Viterbi path through all of this blue region. Yet somehow it still seems reasonable that we should be able to do that, since the fact is that the information we need to actually recognize this word is actually there in this masked version.
You said 60% was carefully masked out. How did you decide which 60%?
So essentially I have a very basic monophone acoustic model. And essentially everything that is left in black are regions where the monophone acoustic model had low entropy, so where it was very confident in what it was predicting. All the regions of maximum entropy, the regions where the distribution across the phone states is flat, it's been masked out.
Oh, I see. But you selected.
Yes. So as I said, yeah. So I've actually, this is what Patrick actually I was just talking about. Patrick, when he came in, is that if you randomly chunk out a bunch of this, you can't necessarily understand it. I imagine there is a random sort of selection where you'll be able to understand it, but you're not guaranteed it.
Well, there's a very famous set of experiments, I think, on the Temporal, where I think Ron Cole's group did, or the Victor's group, one of those. You actually mask out all
Yeah,
the consonant. You
but-
can hear
but they-
everything perfect. If you mask out all the vowel, it's gone.
Right. But I think in those cases, the one thing that I wanted to sort of make the point that's slightly different here is that in that case, I think they're masking out with noise, right? So they didn't send
I see.
signal to 0, they put in noise, right? And so there, that noise is essentially a fricative, right? And so that can fill in. Here what I wanted to say is that I literally just took it out, and that there's no chance that the Viterbi decode is going to make it through these big sort of silence blocks, okay? Yeah. Okay.
But did you do any experiment where you compress the whole thing in terms of temporal?
Absolutely no.
If you do that, you screw up everything up.
Okay, that's a good.
Because time is important.
Yeah. Well, okay. Well, that's what I'm going to argue. So there's also some science behind the science behind the notion that having sparse representation is a good idea. So on the sort of production side, there's this whole sort of history of Ken Stevens and landmark-based speech recognition, and the idea there is that you're trying to look for these points in time in the speech signal that your articulators are doing something of note. And so as you're going through the speech signal, you see, okay, at this particular time we saw a formant shift here, that's a particular time of note. These are the sort of information-bearing elements of the speech signal. And so not only which of these types of acoustic signatures are occurring are important, but it's also important in the case, the canonical case is voice onset time, it's also important the relative timing of these positions. And as you can distinguish between voiced and unvoiced stops by, the time between voicing, when voicing begins and when the burst occurred. It's actually opposite of that. And this is a sort of track of research that hasn't really gotten that much legs because it hasn't really, I think, attacked mainstream enough problems. But, there are a collection of people working on it, and it's a reasonable thing to do from my point of view. On the perception side, there's a whole host of neuroscience experiments. And so this is sort of, generally speaking, the brain is working. It's a big spiking neural network, and spikes inherently are sort of sparse in time. And the level to which these spikes can be sparse is maybe actually a little astonishing. So there's a whole collection of experiments in all various types of mammals and birds that have auditory communication, where they essentially play that animal's communication calls, measure responses in the auditory cortex of that animal, and they find that there are individual neurons in the brain that respond very sparsely in time, so not as a rate code, but as a temporal code, very sparsely in time to very complex acoustic stimuli. So in this case, you have this sort of constant frequency pattern thing. You can sort of think of it as a vowel followed by a burst. This is played to the in this case, it's a bat is the animal, and you see, high response of an individual neuron over 200 trials. If you play just the first bit of that, you get no response. If you play the second bit, you get no response. If you flip it, you play no response. So this neuron is really saying, I like to hear this particular type of signal. It's important to my species communication, and I'm going to detect that and only drop out one spike when I hear it. So, in general, there's a whole lot of work behind this. I don't get into it, but, various people, names that you might recognize, like Shiab Sharma, have, been doing this kind of thing in ferrets. Dan Margoliash, University of Chicago, has been doing it in birds. And there's also a whole sort of host of theoretical neuroscience work that seems to think that sparsity is generally a good idea.
So this frequency there refers to space in the cortex.
No, this is just, think of it as a spectrogram. That's all this is. So you're seeing this sort of formant pattern followed by a noise burst. That's it. And so this is the sort of histogram over 200 trials. So you're not really seeing this much activity per trial. You're seeing roughly 1 or 2 spikes per trial.
And we get to the conclusion that sparsity is a good thing?
Well, so I guess maybe I shouldn't say good. Sparsity is a biologically plausible thing. That's sort of my, sorry. So, sort of taking all these bits of inspiration together, we proposed a sort of alternative acoustic model for speech recognition. The idea is you're going to transform the signal into a sparse set of acoustic events that are somehow relevant to understanding the speech signal. These acoustic events taken together form a pattern of points in time and across various event categories. And then the idea is, given that representation, try to decode linguistic objects, be they words, syllables, multiphone units, with explicit models of the temporal statistics of these patterns. So essentially you're getting these sort of sparse point patterns, and you're trying to say which point patterns correspond to which words. It's a rough idea. So the architecture is sort of summed up here. The idea is you have the speech coming in. You have a collection of acoustic event detectors across a set of features phi sub I. Each one of these detectors will produce a sort of, it will fire essentially at various points in time throughout the speech signal, producing for each one a point pattern in time, n sub phi. All of these point patterns get collected across the different detectors into one point process, what we call point process representation. And that's the representation that we build our word detectors on top of. And then, this was a particular flow chart for building a digit recognizer, but you can imagine that each one of these is detecting a digit, and then they're being consolidated into a lattice and decoded in a normal way. So the first component is, what are these feature detectors? So the first thing you need to do is figure out what your feature set is, right? What is it that you're trying to detect? And we've tried all sorts of various versions of this. Phonemes is the most common. So essentially have one detector for each speech, sound, and language. Distinctive features has also been something that we played with. Individual states of some larger HMM system can be the things that you're trying to detect. So essentially, if you're very likely to be in a state, that state's detector will dump out a point in time. You can also do something a little lower level, where you're actually defining events as local maxima in some spectral representation. So if you see a lot of energy at a particular point in time in a particular channel, you're going to get an event for that channel. Given a set of features, the next step is you want to define a detector function. The detector function is essentially needs to be designed such that it takes a high value when that feature is present and a low value otherwise. So one reasonable thing you might do is say the detector function is essentially the posterior probability of that feature, right? So if these features phi were phonemes, you can say this is the posterior probability of a phoneme for a given point in time in the speech signal, and that's something that's going to go to 1 if it's very likely that phoneme, and 0 otherwise. Finally, given this detector function, you can define your feature detector by simply thresholding that real value here and keeping as the points in time in your point process representation for that detector as the local maxima that remain. And so if this is chosen in a suitable way, that's actually what I see as a very reasonable thing to do, which is you have a posterior probability of a phoneme, keep the point in time that you're most confident that that phoneme occurred, ignore everything else. And that's sort of what you saw in that speech signal that I played for you.
So what is your time resolution for the event?
So the time resolution, so the nice thing about this formulation is that if you notice, intentionally, each of these detectors are drawn independently. And this representation, when they're sort of brought together, is already to the point where these events are represented by real valued times, right? And so each one of these detectors can be operating at a different scale with a different clock rate. You can sort of be as creative as you want here. And the idea is all of those sort of, that asynchrony.
So you have in the R here will be limited by.
Yes.
Will be limited by
Absolutely.
You
Absolutely.
there, right? So
Absolutely. Absolutely.
So you have a bunch of examples, HM states, STR bands, and phones. You try any of those?
So I'm going to go through this. Here's example 1. So this is phonemes, right? So you have on the y-axis a set of phonemes. This is just the state emission densities for just standard phone GMM that you'd be doing a Viterbi decode through. For example, if you had transition probabilities on these phone states, you can say, and essentially your decode of the speech is going to be what's my optimal path through this. This is standard speech, very vanilla speech representation. This can be converted to a posteriogram, which is the posterior probability across the phone set as a function of time by just using Bayes' rule. And then essentially, given those posterior probabilities of each phoneme independently, we just keep over here the times of the local maxima above threshold 0.5. Right? So the idea is, if you see a point here, it means this was a local maxima in the corresponding row over here. And the posterior probability of that phone at that time was at least 0.5.
So in that case, the resolution probably 10 milliseconds.
Yes, absolutely, absolutely. The thing to note here is that, right, so.
Does local maximum mean just with respect to its neighbors,
Yeah,
immediate neighbors?
yeah, no, just immediate neighbors. So this is why you see that you get, for example, here, there's only one SHA here, but you see a lot of events occur because I'm keeping all of them. This is an ongoing argument that I'm having with Hynek, Hermansky as very, yeah, right. Well, so we actually have a student working on, various filtering, various defining, refractory periods for these events, so they only see one per, and that's something that we're sort of pursuing to see whether that can help.
The whole point of this kind of framework is that you can actually have much finer time resolution for some special events.
So you can. It's not being demonstrated here. So yeah, well, so this is the thing. In the first paper I wrote, which is very much in the sort of landmark-based sort of spirit, it was doing distinctive feature detection at the manner level, so essentially broad class detectors. Each one of those detectors had its own scale and clock that I went optimized very laboriously by hand to figure out what the optimal scale and rate was for each sort of broad class of speech sounds. I sort of abandoned that as I sort of got more and more practical in my work, and I hope that you'd find that by the time I get to the experiments here, they're a little more practical than maybe what Ken Stevens might be doing.
So you're going to describe how you obtain those posteriors, like how the HMM was built, whether the language model was used and all that stuff?
Yeah, so in this case, there's no language model. This is just the emission density.
But there's no constraint, left to right constraint?
No, not at all.
So presumably when you actually decode, you do include the language model somehow.
So I haven't done large vocabulary recognition experiments to really get into that. Yeah.
This is just a bunch of GMM.
Yeah, that's all it is.
So they could change from the first state of one phoneme to the third state of another.
So in this case, it's an 8 mixture per state, and it's just a single state per phone. It's very simple.
Single state.
Very simple.
They're context independent?
Context independent, yep. Yeah, so think of this as the simplest acoustic model that you can put down.
Did you try to look at this from the information theory point of view?
To try to reduce this to events where somehow you have...
How much information did you lose?
No, I haven't. The closest thing to that, which is not information theory at all, is just sort of saying, here, right, you have in this representation when you're doing Viterbi decode is just, the amount of information just as real numbers, right, is 6,000. Right here you have 57 real value times. Now, in terms of what's important information, what have actually lost in terms of significant information for the speech, that's just been checked experimentally. Right?
So this is just coming from the standard HMM recognizing,
yeah, not even. I mean, it's just coming
and
from...
then you just count the threshold to get that one.
Yep. Mm-hmm. Yep. Okay, so one sort of slightly different view on what's going on here, which I think is potentially interesting, is what it actually means to have a vector time series representations, that is frames, say MFCCs. And when you have a given speech signal, those MFCCs define a trajectory in some 39-dimensional space, where each sort of, the trajectory sort of shown schematically here is this line, and then each dot corresponds to when we're sampling a given frame. And they're not uniformly spaced because the velocity is actually a time-dependent thing, right? So now, in this particular case, I drew 3 phonemes, right? 3 phoneme centroids, right? So think of these as the center of each of the Gaussian mixture models for these 3 phonemes. And essentially what we're keeping in this point process representation is only the times at which this trajectory has its closest approach to each of these states. So if you imagine you're speaking, you're sort of going from speech sound to speech sound, trying to hit various articulatory targets. You're essentially trying to convey to me that I hit P1, I hit P2, and then I hit P3. It doesn't actually get perfectly realized that you get some, sort of path that going through here. And what we're saying is all that's important is when you sort of got the closest you can get to you're trying to produce P1, when you got the closest to P2, and so on. And so now you have a representation that's just these 3 times marked with which phoneme category they corresponded to. So you can think of that same kind of thing. It doesn't matter what those categorical centers are. They need not be phones. They can be HMM states. And in this case, we have HDK digit recognizer trained up on clean Aurora data, which is just unsampled TI digits data, where you have 11 HMMs for the digits, plus 1 for silence. And each one of these guys has 16 states, I think. 16 states, so you have a total, and silence has 3 states, so you have a total of 179 states. Each one of these states is a Gaussian mixture model, right? And so essentially the idea is that those individual HMM states are defining these categorical centers from which you can just go about in exactly the same way and produce a set of sparse events in time. And so you notice here in this case, it's actually become even a little more shocking how much we've thrown away. You went from 26,000 real value that you have to process in Viterbi down to just 69 real value times in the sparse representation. How do I? Yeah, so in this case, it's the same way, and this is not necessarily optimal, but it seemed to work okay, which is compute a posterior probability over all of these states, just again using Bayes' rule in the same way I did with the phonemes, and then just keep points above posterior probability of that state of a half that are a local maxima in time. That's it.
So when it's a real value time, that means...
Yeah, so let me just actually... so when I say... So they're not technically real value times, but the model is treating them as such.
Okay.
Right, so they could be arbitrarily...
In the middle of the frame.
Yes, absolutely. So they're technically integers, but at the end of the day, the model, as far as the model is concerned, they could be any real value number. The one thing that's important just to emphasize, because some people tend to sort of misinterpret this is not a sparse version of this matrix. In other words, this is not a binary valued or Boolean valued matrix where you have in every cell either a 1 or a 0. This really is sort of stored in adjacency format, like as a postings list, right? For each one of these, the detectors, the events, the points in time at which an event occurred. So it really is a very small amount of information. The third example, really quickly, I'll try to do this quickly, is using something much simpler, or sort of much lower level, not necessarily simpler, which is building event detectors based on individual channels of a acoustic front end. Right? And so in this particular case, this is built on top of the cortical model that Shihab Sharma and his former student and postdoc, Nima Mesgarani at University of Maryland, had been working on for a long time, where essentially each one of these channels in this representation is a spectrotemporal patch. In this particular case, each spectrotemporal patch is a 2D Gabor filter. And essentially, all this is the output of the 2D Gabor filter as you pass it across the speech. So essentially, one of these channels might be looking for sort of slow modulations in time, slow modulations in frequency, and trying to just see when you see that particular kind of pattern to exist. Thresholding this at some suitable threshold and keeping just the remaining local maxima of this gives you this, point pattern representation. Not quite as sparse as the previous ones, but the thing that's significant about this is that here you have a 4,000 dimensional vector time series, which is too high dimensional to do a lot of standard speech things with. Normally they use PCA or something to try to get the dimension down. What we're doing here is effectively getting it down with this sort of sparse sampling, down to such, in this particular case, on average, as you go across this, only 100 of the channels are active at any given point in time. So we've sort of effectively done a kind of very crude dimensionality reduction from 4,000 to 100, and now we can have a more reasonable amount of representation to process with our models.
Does it really do dimensionality reduction? Because you have 100 numbers, but you don't know which dimensions they correspond to. You'd be reduced to models that are rank-based. The rank of the first is something. The rank
Yes.
of the second.
Well, so it's kind of what I'm getting at. I don't have this sort of precisely formulated, but it's sort of what I'm trying to get at with the fact that it's dynamic in the sense that you can, in theory, have access to information in any one of these channels at any point in time. It's just that which ones you're actually, sort of having access to is dynamically changing through the speech signal to sort of focus on what's important at that given point in time. Okay, so given those representations, now the next step is how do you build a model? And so this is where sort of statistics come in, later where machine learning will come in. And the idea is pretty simple. This is just sliding. You guys might have heard of sliding model keyword spotters. That's essentially all we're doing. Is you have a window of some duration, say capital T seconds, that you're sliding through the signal, and you're looking for points in time in which that window contains something that's consistent with a word or a syllable, or whatever it is you're building a model for. So again, you have the speech coming in, set of acoustic feature detectors producing our point pattern, and here you have the model, which is used to define a detector function. So to formalize this a bit, you start with defining an indicator function of time, theta, which is sort of the underlying oracle truth of the signal. It's taking a value 1 at times when the word occurs and 0 otherwise. Next, we define r sub t, comma, capital T, which is r restricted to the interval shown here. So essentially r restricted to our candidate interval at time t of duration capital T that we're testing at a given point in time. And given that, we define a log likelihood ratio detector function that's meant to mimic what this underlying truth theta sub w is doing. So essentially the idea is this is showing what is actually happening, and you're trying to come up with a detector function that would be somehow mimicking that at test time. The log likelihood ratio, it doesn't start off in this sort of integral form. It gets there, but to keep it simple, essentially amounts to having a log likelihood ratio between the likelihood of our observation and our given candidate window, between t and t plus capital T, the observations that we see in that window having been generated by the given word divided by the likelihood that it was generated by background. And then there's this third distribution, which is the distribution over durations of the given word. And so that duration becomes a latent variable, which is where the integral comes from. And at the end of the day, you're sort of considering all durations of the word, sort of modulated by their probabilities, and you're sort of testing the model in each one.
But I thought that number 1, that would be the continuous function to indicate the probability, posterior probability of the word occurring, rather than indicate the function 0 and 1. Oh, it's a real value from 0 and 1.
No. This is indicator 0 or 1.
To indicate whether the
word occurred. So essentially, you're trying to come up with a detector function that is mimicking that ground truth,
with a 1.
right? And so it just ends up being that indicator function becomes the. It's just how we rewrote it down. It's not that important in terms of the actual model. Okay, so we have 3 models we need now, 1 for the word, 1 for background, and 1 for the distribution over duration. This we just estimate from the duration of our training examples. So we just have a bunch of training examples. We figure out the durations are and estimate this in a reasonable way. For the word model, we assume the point patterns in a given word is generated by an inhomogeneous Poisson process, right? So this is essentially memoryless point process that each event that's produced is independent of all others, and that at every point in time there's some rate parameter or spiking intensity function that says roughly speaking, what's the probability that we're seeing an event at this differential time element dt at that given point in time. So the idea is your sort of pattern that you're seeing in a particular interval is being generated, each one of these detector lines is being generated by this underlying Poisson process, which is sort of dumping out events according to some underlying probability distribution in time. So essentially, to deal with duration, once we condition on a particular duration of the word, we normalize out duration, essentially. We map all of our events down to the interval 0, 1 and build just one model for all of our cases mapped down to 0, 1. And you end up with all of these assumptions with a pretty straightforward form of the likelihood shown here. And this just amounts roughly modulo some constants on the outside. The product of this lambda, this rate parameter function, evaluated at all of the events that you see. So a very simple model. These rate functions can just be estimated either with a parametric model, which you'll see in the next examples, where they also use kernel density estimation, which seem to help a little bit in experiments. So to sort of better understand what's going on, I think it helps to look at a picture. So you have phonemes on the y-axis. So this is, again, a set of phone detectors, like coming from those 8-component Gaussian mixture models. And for each row, you're seeing this lambda of t, right? This sort of roughly thinking, what's the probability of this process dumping an event at that given point in time for that particular phone? This is the model for the word greasy, right? And so you see, like you'd expect, initially you'd see high rate of activity on the G detector early on, followed by high rate of activity on the R detector, E, S, and so on. One important thing to note here is that you see not just one detector active at every point in time, you also see activity both on the Z and the S, sort of here, because some people say greasy, some people say greasy. So the point is that this model is actually modeling what it's seen in the training data. So essentially, you have you're modeling all of these confusions implicitly in the representation. And so the idea is, given a particular example at test time, so here's one particular example of what the events are for a given instance of the word greasy, you're asking, how likely was it that this underlying point process generated this particular pattern? That's the word model.
I have a question.
Mm-hmm.
So under this model for the word, if someone were to modify the speaking rate to sound more clearly,
mm-hmm.
like a human would recognize greasy,
mm-hmm.
Would that break this model? Or
So I think it could potentially be okay so long as that duration of greasy, that speaking rate.
Emphasizing the vowels and the consonants stay the same rate. So the relative proportion of the lengths of the sounds is different.
Right. So I think so long as you've seen something consistent with those statistics in training, yes. If you haven't, then potentially not. Because the assumption here is that we've normalized all duration out in this very kind of stupid uniform way, which is not going to be necessarily right in practice. Or sorry, in theory, in practice, it turns out to be generally okay, because there's enough sort of slop in this model to handle a fair amount of variation. You see that these sort of peaks in these lambda functions aren't that tight. I mean, we're not really getting it down to, an individual point in time. It will depend, I think.
So in terms of model parameter, for each word, you have a set of Poisson density.
Yep. So essentially all you have to estimate is this function of time for each one of these detectors for a given word. In this particular example, we're using parameterized form of lambda of t, which is piecewise constant. Right, so you see that this looks kind of blocky. In that case, you have a lot of parameters here. Most of them are 0.
How many examples of that word did you need to train that model?
So we've done experiments. In this particular picture, it was 400. But the model stays pretty stable down to about 10. If you move to kernel density estimates of these lambda functions, it's even better.
Is this because it's an SA1 that you use greasy?
Yes. Yes. Yeah, you need, and that's where the 400 number comes from.
So I think here you use the phone as the event detector. If you use a triphone, you probably can do all of that.
Yeah, so I'm going to come back to that in a second, because there's another really neat benefit of this model in terms of efficiency. I'll get there in a second. So for the digit case, where we have these HMM state detectors for each of our digits, this is what you get for the model for 7. So just as you expect, you start with the first state of 7 with a high rate of firing, sort of progress through in this kind of blurry way through the states of the model. The prosody of, well, maybe prosody is the wrong word, but the sort of durations of the individual phones are essentially shown by the fact that this is not a straight line. If every phone were the same length, this would be a straight line. It's not. The other thing is you're noticing that you're getting confusions again that are handled by the model, right? At the beginning of 7, you have confusion with the beginning of 6. That makes sense. At the end of 7, you have confusion with the end of 1. That also makes sense. So it's all sort of just being captured in this very explicit model of what you see from these detectors in that particular window. Now, this is kind of probably the coolest picture, but I don't have too much to say about it. This is what you get from those STRF detectors for the word greasy, and you see that there's a lot of structure here, you can actually, there's more filters in this case than there are lines of resolution, I think, and so you can't really.
So fraction of word duration, I try to understand why. You say it's so important. So, so this axis indicates the fraction of.
Yeah. So the reason why it's fraction and absolute is I've normalized all of the examples down to the unit interval.
Oh,
so this is saying,
time,
yeah, this is essentially time, but it's normalized. Yeah.
Does this look any different for any other word?
Absolutely. Oh yeah, no, absolutely. There's a whole. No, there's a. I mean, if you blur your eyes a little bit, and it's maybe not the best. Yeah. So there's a sort of X here, but it's not symmetric, sort of across here. Yes. So this would be S. You also see that there's this kind of. I should say a little more about this. This is a set of Gabor filters, but then you have the real filters, the imaginary filters. The first 2,000 are the real. The second 2,000 are the same thing, the imaginary version. And you see that that those things aren't symmetric, that there's structure up here that's not the same down here. So anyway.
But if you look at this one as the frequency index, a filter index, it doesn't involve frequency.
No. There's a whole lot going. So these are a set of spectro-temporal modulation filters, essentially, which have four-dimensional parameterization. They're very complex. So there's a lot of sort of inner loop stuff happening as you go through here, so you can't really interpret it. That's sort of the problem with it, actually. Okay, for the background model, we just assume that when you're not in a given word, these detectors are just spitting out some background rate of activity. And so that's all we assume for the background rate. It's just a homogeneous Poisson process with constant lambda, or in this case not lambdas, but constant background firing rates mu for each of the detectors, and that gives you a simpler version of the likelihood for the background model.
So think about this one as spontaneous.
Yeah, just what you sort of see on average across all your speech from that detector, right? And so as you're sliding this model along, you're saying, is this pattern I'm seeing more consistent with what I expect for greasy, or is it just better to just call this background? That's essentially the model. Okay, sort of early experiments with this as a keyword spotter. You have a point process keyword spotter built from 8-component phone GMMs, monophone model, trained on all of the Timmett training data, right? So that's where we got the acoustic model. We trained Poisson keyword models on 4 speakers. We test on a distinct set of 3 speakers. And so it has more details. For the baseline system, we build a simple HMM based keyword filler HMM keyword spotter, which is essentially just the path for every pronunciation of the keyword tied to a phone loop. And we use the same exact phone GMMs here. So it's essentially doing Viterbi decode through keyword plus background model versus doing Poisson process decode of keyword versus background model on the events. So here are the results. So we have 20 keywords. They're sorted by the performance of the point process model. You see that the... No, I don't know.
And the PPM doesn't learn the language models?
No. I mean, it learns the internal structure of the word, but you're evaluating this model in a particular window in isolation from everything else. Yeah. So there's no context whatsoever beyond the internal sort of phonetic structure within the word. So you have a phonetic language model, but nothing expanding. This is, so 20 keywords. Performance varies wildly. They're sorted by point process model performance, and you see that the thing that pretty much predicts performance the best is the duration of the keyword. The HMM system does pretty much the same. The averages are comparable. But the thing that I think is most interesting and was sort of promising at the time is that we essentially have 2 systems. One is operating on sparse. It's doing about the same on average, but you get very different performance at the keyword level. Right, so some cases we're way ahead, some cases the HMM is way ahead. So we have 2 systems which are fundamentally doing something very different, even though they're based on the exact same GMMs. Right? And so the idea is that the hope is that, sort of from point of view of system combination, which I'll have some results from the workshop this year, that's maybe a useful thing. The other thing to note is that we didn't essentially build a sort of poor man's HMM system by throwing away this information. We have something which is somehow different.
Did you have an intuition of why yesterday works very well for HMM?
The funny thing about keyword spotting is that the performance is a little idiosyncratic. Like, one model will have an issue with one word that it just this is something called keyword spotting figure of merit. which is essentially the area under the curve in the first part of the RC curve. Yeah. So, essentially what will happen is, in this case, say, we're doing, for Congress, we're doing much better than the HMM systems because the HMM had, I think, the word caucus that it confused a lot for some reason. So they're just sort of idiosyncratic cases, but that's exactly what helped us, I think, in the summer when we combined all the systems.
But you don't know really why.
I mean, I couldn't give you, no. Yeah. Just really quick, this is sort of a larger, I don't have baseline experiments for this, but this is something I did in the summer where using the multiphone units that Jeff defined from his mutual information criteria, we have detectors for each of the multiphone units. So some of these are words, some of them are single phones, some of them biphones, and so on. And in general, I was able to get with this model reasonable, although there's no baseline, so reasonable is hard to define, reasonable performance. So here you have one dot for every one of the 4,000 models. You have on the y-axis 1 minus equal error rate, so it's the accuracy essentially. And down here you have the median phone duration, and you see that in general it's doing what you would expect. The longer the unit, the better it does. The more training examples, the blue dots are the cases where you have at least 400. Red are when you have less than 400. The more training you have, the better, and so on. Okay, so.
Why is it better for only unit? Is it a question of having too few points? Or is it something to go with?
Well, it has to do with sort of just poverty of stimulus, right? I mean, if you need a bunch of, you estimate a bunch of parameters, you just need to have enough examples to learn them.
So it could be that, I take a sampling rate that's 10 times larger, and then I get more of these spikes.
Mm-hmm.
Right?
Mm-hmm. Yeah, so I think you can't just arbitrarily, so you can make an argument that you just somehow take a given spike you see and just randomly sample around that. I think that's equivalent at the end of the day to
So, is it, if I take the sampling rate 10 times larger, I have more points to estimate the lambda of the rate process, right?
well, so I would claim that the detectors with a higher sampling rate don't necessarily mean more spikes unless it's very noisy. But then that's not really sort of, I mean, all you're doing, right, is just, you're sort of in a very predictable way increasing the statistics. It's not necessarily going to give you more information about what you'd expect from the word. Right? I mean, it's equivalent sort of to coming up with a sort of lower resolution parameterized version of the rate functions, where you make some assumptions about what you expect them to look like, so that if you only see one example, you can sort of fill in a whole Gaussian, say, as opposed to just estimate one point. I think that's sort of what you're suggesting, and I think that's the case. When you have a sort of simpler parameterized model, say these lambda functions were, these lambda functions, instead of being piecewise constant, we assume were a mixture of two one-dimensional Gaussians, right? You'd have 4 parameters instead of 10.
But the question is the evaluation, really. Right? When it comes to the evaluation part,
Mm-hmm.
Building the model is fine as long as you have enough, G-joint. It's during the evaluation that you have one spike that's going to determine the score.
I see what you're saying. So I think what would happen is if you applied that, if you actually look at the structure of the detector function, that likelihood of the keyword, essentially what you're doing is adding a number in log form. You're adding a number for every event that you see. If you do something very predictable that's just going to increase the number of events by 2, right? It would give you sort of the same events with the same sort of distribution in time. You just have twice as many. It's going to add a number to the numerator in a very predictable way. It's going to add the same number in the denominator, and you end up with the same likelihood ratio.
Yeah, obviously it can't be that predictable.
Yeah, but that's a good question. I mean, what I've been arguing, I mean, there's a reason why I'm arguing this whole business with Hynek about should you smooth these guys before you define events, which is, do you really want to be beholden to the variability that you see in this?
Another thing is, you can decrease the threshold, and so you get more spikes.
Yeah. Performance varies with that. I mean, you want these, there's a sort of optimal point, you think, where you want these sort of...
Does this be the duration?
Would this be a...
Does this help from shorter words?
Yeah, no, I mean, I think that's I don't have the answer. Yeah. Okay, so I have a live demo of a keyword spider. I'm choosing an easy long word. This is the word Massachusetts trained. with a timid acoustic model. And the examples of Massachusetts came from newsreader BU radio speech. And now I have this microphone in this room. Okay, so I'm going to start just by reading. I have a paper that I have here just so I can have something to read, and I'm going to pepper in the keyword randomly. Yeah. So,
when it thinks that you said it.
yeah. So let me explain this.
So you're trying to say Massachusetts?
Yes. See, it had some activity. You're a little far. But the idea down here is that you have essentially the representation. Each row is a phone detector, and you're seeing a point sort of real time with a delay. And I should warn you, there's about a delay of about a half a second, just how I wrote it. And on the top, you have the signal in blue, and then the detector activation. So that log likelihood ratio, lowercase d sub w for the given keyword. Okay. And so if I say, several strands of research in the fields of linguistics, Massachusetts, speech perception, and neuroethology suggest that modeling, and I hope I got it. Okay. Suggests that modeling the temporal dynamics of an acoustic event landmark-based representation is a Massachusetts plausible approach to the automatic speech recognition problem. Did I get it? Okay. So in general, Massachusetts works really well. I have...
Massachusetts.
Yeah, so unfortunately, there's a point at which...
Massachusetts.
Massachusetts.
You get closer probably.
Massachusetts.
You got to talk to your microphone.
Indiana.
Yeah, got it.
Wyoming. Tennessee. Massachusetts.
Well,
We're not speaking to the microphone.
well, so there's no British accents in timid. At any rate.
Well, I knew your accent.
I was trying to think what the Boston accent version would be.
Now, to give you sort of, I'll just play really quick a different word. So if you see what I'm typing, it's the word greasy. And this one, just again, the way I wrote it has less of a lag because it's a shorter word. And several strands of research in the fields of linguistics, greasy perception, and neuroethology suggested to get it. Oh. Oops.
Job. Oh, shutting down.
Oh, there you go. Okay. Several strands of research in the fields of linguistics, greasy perception, and neuroethology suggest that. Did I get it?
Twice.
You got
Yeah, they got
60%.
it twice.
I got it, yeah. So that's the thing, is with greasy, you'll see quite a bit of false alarms, which is why I don't lead with greasy for that reason. Anyway.
So that's speaker independent.
How
Yeah.
like on the Massachusetts, is it like, what happens with like fragments? So like you said, NASA.
So you'll start getting activation as you go across, and then it'll just stop. And so essentially, as you go through, you're building up evidence. As you go through the word, that's sort of accumulating to this detector score until, it hits a threshold, and then it shows the word at the top. Yeah. Mm-hmm. Yep.
So you don't have the greasy, you don't need to have the word in the training set to do that. Everything comes from the phone combination.
No, you do. You need explicit examples of the word to learn from.
That's all. In principle, you don't need that.
No, but in
Yeah.
theory, that's interesting. You could patch together
Yeah.
phone
with
and
the
Oh,
phone plus on.
So what I would claim is that in that same paper with those BU radio experiments, we had two versions. One was whole word. One was delayed coincidence of syllable detectors. So essentially, you detect the first syllable, you detect the second, then you fire the combination of the two, and that worked just about as well. Yeah.
Greasy probably is in Temic. They have every single sentence. with
Yeah, greasy. Yeah, greasy's fantastic.
Massachusetts not there.
Massachusetts came from the BU radio data, so that's Boston University, so there's a whole lot of Massachusetts too. Okay, so I'm going to try to speed up because I imagine it's getting pretty... okay. How much time? Okay. Okay, so now the question arises of computational efficiency. I made a claim in the title that we have reason to believe that this will be more efficient. It's maybe not that far of a stretch if you just think about it for 1 second, that we're processing much fewer number of values in our representation, that you can maybe make things a little faster. We saw in this case you went from 6,000 real-valued likelihoods. The Viterbi decode of this guy is going to be linear both in the states and frames. This guy decoding this thing, even when you're sliding a model across and evaluating at every frame, it's going to be linear in the frames because you're sliding. But then the second thing that it's linear in is not the states, but the number of events, right?
You computed the posterior over all the HMMs to get that.
Yes.
Right.
So that part is going to be matched. Right, so in other words, that's the same amount of work. Now the question is how long does decode take? Okay.
I guess the question is how long does that part take with respect to the rest? It's probably
It takes a huge amount of time. Yeah, in fact, that keyword spotter that I showed you in Java with not a particularly sophisticated implementation, the decode, you can do hundreds of words in real time. The front end is taking all of the time. It can happen on this machine, but just barely. That's largely due to the fact that Java happens to have really poor support for matrices and signal processing and so on, and I wasn't about to rewrite all that. But anyway, the idea is that, just you have this detector function. All you're doing is adding a number to your score for every event that you see. That's all the work is involved. Now, what you claim is that work you do up front on the front end, that's fixed, right? That's going to be the same for every word that you process. Where you get the benefit is that when you have, if you want to process 10,000 words at the same time, you only have to do the decode part for that, right? And so if you wanted to be running a bunch of detectors in parallel in real time for all of your words, that's where you're going to get the benefit. Now the thing that Lee mentioned earlier is this notion that if you go from monophones to context-dependent triphones, say, the number of states is going to start ballooning, right? You're going to go, order 48 cubed. If those states are largely mutually exclusive, that is, you can only be in one particular context of a phoneme P at a given point in time, the number of events is not going to grow that way. Ideally, the number of events would stay exactly the same. So you can go from a very simple acoustic model to a very complex acoustic model and still have the same computational burden. Now, if you imagine you have like 200,000 Gaussians, like in these modern systems that IBM and BBN builds, all of those guys can be individual detectors that you're building your model on top of, but the events will be just as sparse, or largely just as sparse. Well, they will be quite sparse. But the point is,
all contexts of a phone sound the same,
so
right? So you have to fire them all simultaneously for it to work.
right, but if you set thresholds on the detectors correctly, it can be the case that you are restricted to just only one or two that are actually the most confident that are going to make threshold and produce an event.
Actually, that might be a place to have them non-independent.
Yes, so non-independence is coming up in the discussion of the thing. But yeah, you're absolutely right.
Triphone, by definition, they are dependent on, because if this phone, requires the left context of this, and the other phone requires the right context to be the same.
Mm-hmm.
So somehow there's a fairly complex dependency.
There definitely is, and where I should just start before I get to the later part of the talk is that all those independence assumptions are terrible. I admit that freely. You got to start somewhere. Right? So what I should say just really quick is that so far, Hinek and I are working with a graduate student at Hopkins who's built over the summer a keyword spotter, unfortunately in Java, but it's still pretty fast. It's able to do 1,000 words in real time on just one machine. And we think that we can get that number up, hopefully. Okay, so that's all I'm going to say about efficiency. Now onto robustness. That's the main claim. And so the argument that this thing should just be inherently more robust is pretty straightforward. It's just simply saying if somehow I can claim that the most confident part in a posterior probability of a phone, the point in time which is most confident, is the thing that's going to be most stable when you add noise to it. That's the intuition. That's pretty much the assumption. The experiments show how true that is. Here you have the posterior probability of the phoneme ta as a function of time through a bit of speech. The blue line is clean. The red line is in 20 dB, I think, white noise. And you see that this frame level trajectory of this posterior probability changes quite a bit. But the thing that, in this particular case, that remains the same is the time of the local maxima. You could have the case that the amplitude of the local maxima drops, but still the time value of the local maxima is somehow invariant. So if you build a representation on this, you're going to have something that's more invariant than on this. Now, given that this amplitude can drop, and it does, it becomes less confident in noise, you need a way to somehow deal with the fact that I'm making this hard threshold decision. And so this suggested a very simple adaptation strategy where the idea is you're going to continuously vary each of the detector's thresholds, firing thresholds, to maintain the background rate, those mu values for each detector that you estimated in clean speech. So if you expect to see this detector doing something at a certain rate on average in clean, and now you add noise and it somehow all of a sudden stops, or it all of a sudden starts going really crazy, you're going to want to adjust the threshold to keep it at sort of an even keel. And so on the right we have the background firing rate as a function of the detector threshold, right, for both clean and in 10 dB white noise. And this is for the phone detector for right? So as you add white noise, it says, this doesn't seem like a vowel anymore. Let's be less confident of vowel, right? So what you need to do is drop to the threshold from, in this case, say from 0.5 to like 0.28 to maintain the background rate that you saw in clean. And that's all you're essentially doing. And there's some strong assumptions here that first the times of these detections and the relative strengths of these detections are somehow preserved under noise. So that's the main assumption, which not necessarily the best. But the other assumption is that this background rate is an adequate statistic to adapt with, which is also not necessarily a great assumption. But the most important thing that's useful is that this method that I just described is completely unsupervised. It's just something that's just happening. You can just have this little sort of process, just keeping an idea of what it saw recently on average, and sort of adjust these thresholds accordingly.
If you have the background normalization.
What?
If you have a background normalization,
Mm-hmm.
you're adding as much in the numerator as in the denominator.
Yeah. So the idea here, that's not entirely true, right? Because each of these detectors, it's not just one universal threshold. You have a phone dependent detector threshold, right? So I think that allows it. And I have to think about that. It's a good question, but it does make a difference. So we'll see.
I suppose when it's noisy, all the detectors may start looking like everything on the same, right? Yeah, it's very, very noisy. You may want to change the thresholds because of that.
It sounds like it makes sense, but it also sounds like, on average, it would have the same effect in the numerator and the denominator, but you're computing the likelihood ratio.
Right, but probably the detectors, when it's really, really noisy, for S, they all about the same.
Mm-hmm.
So you need to change the threshold.
Well, I thought the robustness issue here is not just a matter of threshold, right? Because noise actually scrubs some of the acoustic model, so it makes detector kind of testing to become more difficult.
Yes, so that's simply true. But the assumption here, and it's a limited assumption, is that you can mess up things a lot, right? And it maybe affects the acoustic model, say, for a given phoneme in a very unpredictable way. But you would still hope that whatever it's done, a detector for will still achieve a higher value during than it would something else. And that's the thing that this is built on top of. Right, so long as somehow that pattern can warp, but so long as the peak that happens in the and the S are still,
so eventually still come down to discrimination.
Yes. But it's a limited assumption. So here is a sort of early experiment with this. This is with just keyword spotting, where we added various levels of white, pink, and babble noise. We have adapted point process model keyword spotter, adapted HMM keyword spotter, where the HMM adaptation was just done with MLLR. And in fact, it was supervised MLLR because I couldn't get, in the case of noise, to get the supervised, unsupervised stuff to work.
So why does the HMM performance drop sometimes with adaptation considerably?
Because that MLLR, right, is kind of, it's like an EM thing, sort of, right, in the sense that you're trying to. It doesn't necessarily find an optimum, I think. It's been a.
But it's supervised.
It's supervised on training data. Oh, the other thing I should say here is that this is with a very small amount of training data. So if you had plenty of training data, I agree that you can learn a very solid linear transformation. If you have a very small training data, that linear transformation can.
Is this one transform for noise type or for noise for SNR?
One transform per noise per SNR.
But you don't have a lot of data for it.
I don't have a lot of data.
You do a time speed or something.
Do I do?
You don't have a lot of, you need to batch up the
So essentially you assume that I have an existing acoustic model in clean, and now I have a little bit of noisy data which I artificially added noise to.
Depends on how much people is people.
Yeah. So you know, in this particular paper there were curves showing how much data you have and the gain that you get, and essentially what we found is that the point process model adaptation is very stable down to about 10 seconds of adaptation data, whereas the HMM broke under a minute.
But is it the case that the point process model is adapting on the test data, whereas
No,
the
you're given
MLR is being estimated on training data?
No, both of those transforms are estimated on a little bit of noisy data taken from test. Right, so you take a little noisy data, that's your adaptation data, and now you go and adapt your model.
Wouldn't it be
Adaptation using MLR at test time versus
Yes.
your adaptive threshold at test time?
Yes, absolutely.
Okay, so it's like a whole matrix worth of parameters versus a parameter per.
Yeah, right. So you need more data, right? It's all the same.
It would be interesting to like in robustness, you know, like multi-condition training is common. Where you, like you don't know the noise, you just use a bunch of noises and retrain your GMMs. Like it's like the Aurora other set. So I think if you did that with your GMMs, you would then the point processor would learn all the confusions that noisy data with noisy acoustic models. These two phones are confused. But then your point processor model would learn that.
Yes. I haven't done any match training test experiment. I haven't done anything with that. Everything so far has been clean train. Yeah.
And the adaptation data includes the actual thing that you're testing on, right?
Yes. Yeah.
But
So
you could have used maybe block diagonal something.
for adapting the point process model?
Because we know emitter is
Yeah.
too many 400 parameters.
Oh, I see what you're saying, to sort of give it a comparable number of parameters. Yeah, I mean, I think I ended up making this. It's been too long since I've done this to remember what the transform constraints were. I think I maybe assumed it was diagonal. I essentially made it what I needed to make it to get an improvement on the amount of adaptation data I was providing.
This figure of merit, right?
This is relative performance to the clean figure of merit in noise. So this is saying 92% of the clean value.
Okay, so that's
Right.
like over 100.
Right. Yeah, exactly. Okay, and then something very recently that I did was taking these STRF representations, building keywords. And I just did one example. I'm going to be doing more experiments for this soon. But essentially adding, I think in this case, white noise. You have without adaptation, the HMM, the phone point process model detector, and now a detector based on the STRF features. And you see that you get just this absolutely huge gain as you add white noise. And there's lots of sort of arguments for why this is the case. It's sort of a whole active area of research for Shihab and Nima. With adaptation, you see that the gains are even greater. We're really holding up pretty good. So now to come to the first mainstream task. All of this has been admittedly pretty toy. And so this is, again, the Aurora 2 evaluation. So this is clean training. I should put it on the next slide. Oh, I forgot the slides in here. Okay, so just really quickly, the idea here is that you're building a keyword detector for each one of the digits, running them in parallel, and then using their detections to form a lattice, and then doing a decode of that lattice. And our idea is that we're sort of maintaining now with this detection-based speech recognition approach, which I should say is something that was proposed by Chen Li and Hynek somewhat simultaneously. We're sort of building into that sort of detection-based approach where we're only accounting for parts of the signal at the word level that you're confident about. Here, we're sort of only accounting for words when we're confident. We're only accounting for the individual state detections only when we're confident. So you have this sort of very sparse detection-based thing all the way through. The Aurora 2 evaluation you're probably all familiar with. We consider the clean training evaluation, and we have the baseline standard HDK recognizer. This is the simple, I think it's called the simple backend. So this is just 11 digits model, 16 states per model. 3 components to each state's GMM. Okay, so the first result is in clean. What happens, how sufficient is our sparse representation to detect these keywords and do the decode? And the answer is that we take a bit of a hit, but not that much, and I would claim not that much, especially given we've thrown away. Yes, we can have an argument about
5% more errors.
Yeah, well, so that's absolutely true. What I would claim is that the last section of this talk that I'll get to in a minute has discriminative training for this that I think would catch up, but I haven't done it yet. So that's that. Now sort of what's maybe a little more impressive is what happens when you add noise. So we have the baseline HTK system. In this case, it's non-stationary noise. We have 2 examples, Babel and Airport. The baseline HTK system, point process, and then the point process with this simple detector threshold adaptation. And you see that forgetting the adaptation for a second, just throwing away all of that stuff when you have non-stationary noise coming in and out is actually a wise thing to do, given these experiments. If you have a little data with which to adapt, and in this case it was a very small amount, I think like maybe 30 seconds of adaptation data, we're able to get an even bigger improvement. And essentially the results were the same for the airport noise. And keep in mind that all of this threshold adaptation was done unsupervised.
But earlier you showed the keyword detection and this is recognition.
Yes. That's where this is coming from.
So what's the difference? For keyword you need to do denominator, not for recognition.
No, we're still running. We're still running detectors for each of the digits on this in parallel, right? So you have a detector for a keyword spotter for 7 running in parallel with a keyword spotter for 8 and so on.
Oh, okay.
And then essentially all of those detects will define a set of boundaries for each of the words that you construct the lattice with, and then you do decode.
You can do it here.
Yeah.
Okay.
Now, for stationary noise, you run into this problem where the amplitude of the local maxima in the output is going to vary as you add stationary noise, and you really need to adapt. So you see that you start taking a bit of a hit in the higher noise levels with, I guess just in general, you take a bit of a hit in stationary noise with the point process model, but then if you adapt in this unsupervised way, you make it up and then some.
And feedback one. So in the case of clean, you had clean test, you were still behind the HTK simple backend.
Mm-hmm.
And here on the relatively clean samples, you are still considerably behind. So most of the gain is in the really noisy conditions.
Yeah, I would say that's true. I think this whole performance curve in the point process model can come up with a better model, right? This is the first iteration at this model with all the independence assumptions and everything. So my hope is that a better model will make everything sort of rise up. But yeah, you're absolutely right.
Yeah, I'm trying to think how could this model be used for multi-step training. So is that's clean, right?
Yeah. So this is all.
Is trained using clean data.
Yeah. So you could use the model as is with the noisy data, and it will just learn whatever it happens to see these detectors doing. It's not.
Do you have the result for multi?
No. It's just the clean.
For HTK, at least you get 20% higher.
Mm-hmm. Yeah.
Should go up, right? I mean,
Yeah. It will go up. I don't know how.
The HM goes up, this goes up.
Right. I mean, they're pegged to the same acoustic model.
And when you're training your word models, how, maybe I missed it, did you go over how you do the segmentation of the training data to get? So
you need to align your training data to your word model. Force alignment using the HTK system.
Okay.
And that's not necessarily perfect either, right? So I'm giving my system possibly poor boundaries, although I think the boundaries are actually pretty good. I wouldn't claim that that's necessarily a big...
It's all clean speech.
Yeah, right. So I think it's...
Well, the HTK system is a little broken in that you have to align at least, is it 16 frames to the word O every time it occurs? And so you can get, is it like a minimum of 200 milliseconds for that word, even if it's shorter?
I didn't know that's true. That's good to know.
How many times are all
Yeah. That's a good point.
In the simple backend standard for this HTK setup, it's a word-based system, it's not a phone-based system, and every word has a fixed number of states, regardless of whether it's 7 or 2. Or 2.
Yeah, no, that's good to know. I never occurred to me.
So this is predicated on you reproducing the prior on the little segment for each row.
The prior on what?
The prior probability. You set your threshold so that the priors match.
Oh, yes. I assume the priors are uniform. I make no assumption. Actually, so technically in Bayes' rule, you want a prior that's actually the real prior, but I didn't, in fact, do that. What I did was say all the state priors are uniform. Yeah. Making them non-uniform would probably help, but yeah. Okay, so the last thing I want to discuss, and I have time, right? Okay. Really quickly, discriminative training. I've been talking about this. So everything's independent now. That's not good. We have a large number of parameters to estimate. It could be lower. And so the easy way around this, instead of going back to the model, I think ideally one would go back to the model and actually build it by hand to get some nice numbers quickly. You can just bring machine learning to the rescue. So sort of how I've gone about this so far has been in the context of kernel machines. So the idea kernel machines is you want to define a distance between your examples, right? And so what's the distance between two spike trains? It's an open question, right? So I went to the neuroscience literature and I found this Victor Purpura distance, which is essentially the string edit distance between spike trains. So you can insert spikes, you can delete spikes. When spikes are going to be called the same, if they don't align perfectly in time, you have a sort of what I call a translational cost. That's proportional to the amount you had to translate them to get them to line up. That's essentially the distance, right? Given that distance, you can define a kernel, like as in the concept of kernel machines, SVMs, and so on. In this case, just RBF kernel with Euclidean distance between points in a vector space replaced with Victor Purpura distance between spike trains.
So if we talk about this one, for the earlier case, you use the maximum likelihood to train level.
Yeah, yep. Mm-hmm.
But you have multiple possibilities, so you probably use EM. You use posterior probability to weight.
No. That's just simple maximum likelihood estimate of those. Yeah, yep, that's it. Mm-hmm.
Okay.
Yeah. So, right. So then, given that kernel, you can now use standard SVM or regularize least squares. And here I have some results with just keyword spotting various words. So this were the Poisson process model performance. You see, do good on greasy, not so good on year. When you do this discriminative training with the SVM or RLS, they're about the same, and you get some pretty significant improvements, especially relative. So, yeah.
Are you still doing the time normalization of your training data?
Yes.
Or are you keeping?
Yes. Yeah, so one thing I should...
As long as you're doing distance between spike trains, you could keep the original. You don't have to normalize for time anymore?
No, I think that's actually a really good idea. I'm not sure if it would make a big difference. It could actually be somewhat very similar, right? Because one thing to point out about this that I think is actually pretty interesting is that this formulation that you get from representer theorem, right? You get a decision rule that's a linear combination of your kernel function evaluated with respect to all of your training examples, right? So what this is doing is imagine you have this abstract space of words, right, word space, and you have every example that you've seen in your training data of greasy, every example of things that's not greasy, right? You're essentially trying to learn a decision boundary relative to all those examples by using the distance between, in this abstract space, this abstract distance between all of your training examples and now your test example. This is essentially doing exemplar-based speech recognition, but in this kind of bulk way where you can actually do a lot of this computation. This string edit distance thing is now not n squared in the number of frames as it would be to do DTW. This is n squared in the number of events, right? And so you just shrinks the amount of work you have to do to actually evaluate this guy. So you can really just imagine you have 1 million examples of the word greasy populating this space. You're just saying, which one am I closest to? And that guy's going to get all the alpha. And you now sort of identified it in this sort of exemplar-based way. That's what's happening here.
Throw away Poisson assumption.
Yeah, so the one caveat to all of this...
Is the distance.
Yes, yep. The one caveat, well, so I say a couple things. You can train the same Poisson process model, right, which is essentially just those lambdas with, if you think of the case of the lambdas where they were parameterized piecewise constant, that's just some fixed matrix of parameters that you can estimate discriminatively. Those performances are actually pretty close to what I got with this. This is, I think, a little more interesting because you're still keeping around the fact that your representation are times, they can be asynchronous, you get all of the benefits from it.
So there are different assumptions there. One is that you assume that,
Yes,
it's
yes.
independent,
And this is learning the same model where they can be dependent, they can be whatever machine learning.
The other one, you rely on the distance matrix between two trains, which doesn't
Yep.
seem to be really reasonable. I was looking at the train. So you would like to have two, trains
Mhm.
of spikes
Mhm.
that coincide with the
Yes.
the timing. Right?
Mhm, mhm.
But that is not structure built in there. If the pattern has particular property like a refraction period
Mhm.
and all this, then this one probably doesn't make sense.
Why is that? I mean, so essentially, if you're going to build a refractory period, you're going to keep in your representation the first event that occurred, right? You would hope that somehow first event is somehow characteristic of the word, and thus that time that first event occurred is somehow something that you'd want to see again.
So for example, I'll give another example of why this one doesn't make sense.
Mhm.
For example, if you have two neurons,
Mhm.
one has a little bit more spontaneous rate than
Mhm.
the other. It's
Mhm.
already screwed up. But that spontaneous probably does not give you any useful information. So you should treat these two trains to be similar to each other, despite
Mhm.
the fact that this one will be high. So I think this is a brute force counting, which doesn't take into account any properties.
Yeah, that's a good point. I think the sparser the representation is, the better this is. So if you're estimating, so typically what I should say when you have these lambda functions that you saw earlier, typically you're only seeing a couple of events per phone. You're not getting a sort of dense thing where you're looking for sort of rate variation in the spikes. You're sort of characterizing with a rate function what you'd expect to see over many trials, but each trial is only like one spike. Right, and so the assumption here is that the actual individual time of that single spike is somehow carrying information. It's not a rate. It's a temporal code, not a rate code.
Okay.
That's the assumption.
But
You could be right. I don't.
In that measure, if you get some random spikes
Mhm.
for some reason, which is normal, right,
Mhm.
maybe even in your case with some noise, right,
Mhm.
then any distance should discard this random event and then just focus on
Mhm.
whatever information. So you don't distinguish. But this measure,
Well, so you're right, but I think a refractory period would actually help you,
you have that.
right? In the sense that it would throw away all that random junk that happens and just keep the one first time, which somehow is now comparable, right? That's what I would claim. I don't know, I could be wrong, but I mean, not that much thought has gone into this. It's something that seemed like a reasonable thing to try. I tried it, and it worked.
Just a couple more questions on this one. I guess for the different detectors,
Mhm.
you essentially concatenate their spikes.
Yeah,
They're
so
one big
essentially
long spike
you
train.
collapse them and sort, right? So you concatenate and then sort, and now you get one spike train, each spike marked with its class. And you don't allow substitutions across classes.
Oh, okay.
I see, yeah.
So it's ordered.
Yes.
descending.
Yes.
I see. And then if you go to the next slide, so like with the regularized least squares,
Mhm.
the F, I would assume is a weight vector.
So-
What's F of R?
So f is this function, which is a linear combination of all of the kernel functions evaluated from all of your test case against all of your training cases. So it's essentially saying if you have alpha sub I high, it's saying that particular example is a good example to look to if you're trying to tell the difference between.
Oh, I see. So alpha
Yeah.
is what you can adjust
Mhm.
to get that regularization
Mhm.
term.
Yep. Mhm.
I see.
So it really is exemplar-based speech rate. You're trying to figure out which examples are somehow characteristic. So sort of, this is what was done in part over the summer. So Patrick and Jeff have seen this slide already. The idea here is I had a set of phone detectors built on top of Hynek and his students' neural networks. So just think of it, the GMM is the same idea, it's just a neural net. And the idea is I want to now do discriminative training to tell the difference between true examples of a given word and incorrect examples of a given word taken from the lattices. Right? So the lattice will contain true arcs for the, for example. It will contain false arcs for the. And the question is can you take those positive and negative examples and learn the difference just based on what's in the lattice that's already made it through the baseline system? Can you tell the difference? Here we have all of the examples, training examples that I use for a given word, the. Okay? On the top, above the red line, you have the positive examples. Below the red line, you have the negative examples. And you see that there is structure. That in the top cases, you have much more constrained events for various phonemes. In the bottom, you get all of these sort of noisy regions, which can be used to tell the difference. And so here's an example of what. So now this is, again, this f of x for across all my training examples. This is a histogram of essentially the classifier scores using RBF kernel and regularized least squares. And you have the light blue distribution is for the positive examples, the negative distribution is for the negative examples, and at the end of the day you can get an equal error rate of 26%. And this is telling the difference between positive and negative examples on just taken from the lattice. So this isn't one versus everything, this is one versus its competitors according to the baseline system. So first performance numbers, we have scarf performance using unigram language model or trigram language model, and then we have scarf plus point process model where I'm just now rescoring 72 of the most common error producing words. So I'm only doing discriminative training on 72 words and just providing a lattice annotation for scarf just for those 72 words. And you see that in the case of a unigram language model, it starts with 16.9% down to 16.0 unigram to trigram on scarf, and we get most of that back from the acoustics alone without going to trigram. So it turns out these 72 words are typically function words, and that somehow there is information in the acoustics to tell the difference between correct and incorrect function words without having to rely on a trigram language model. When you have the trigram language model, we still get a bit of a gain, but it's not as much, but still significant.
If all those words were right, do you know how big the difference is would be?
Huge. Huge. Yeah, no. So this is no magic bullet yet, but you know the thing is these are already cases where IBM's latest and greatest speech recognizer didn't know what to do, right? And so you're not going to get them all. If you did get them all, you'd be you'd be doing great, right? But they're already the hardest ones, right? So this is saying that you can still get a lot of it with this model. There might be better models, and I challenge you.
Do you have actually your own error rate as a binary class or something?
Average overall, the words.
So what is worse than security?
Yeah. So this let me ask you. This is just for the. The was sort of a middle of the road classifier. There's some of them do much better, some of them do a little bit worse. But I think I chose these 72 words by capping the error rate of the classifier. That is, I didn't want to score things that I had above, I think, 30% or something. Right? So did you have? Sorry.
No, this one.
Okay. Okay. These are the sort of combined overall results now where we have the baseline Attila system plus scarf retraining plus adding this HMM system that Patrick put together to add word annotations plus this PPM 72 word, and you see that you get sort of consistent gains as you go through, and at the end of the day, and that's true also for dev data and eval data, and at the end of the day, sort of all combined, we get about 8% relative and 25% of possible. And this is sort of comparable to the other sort of efforts in the summer. Okay, two just really quick plugs, because Ken Church, I think, would be unhappy if I didn't do this. This is work with Ken. Really quick, he was here recently. Were people at his talk when he was here? So this is just really quick a plug for that. If you guys seen the talk already, then you've seen the talk already. But he's going to be going and giving this talk on my behalf at InterSpeech. And the idea here is to do unsupervised term discovery. So given a bunch of speech, how do you actually figure out terms of interest? It's sort of the orthogonal problem to spoken term detection. The idea here is you want to detect the words, but you don't know what they are yet. At the end of the day, we had sort of this dot plot method to do it. And the main result, essentially, is that compared to the prior art, which was worked by Jim Glass and one of his students, Alex Park, from a few years ago, compared to the prior art, we're able to do this about, I think, around 400 times faster. So we can search for all repeated terms in speech in 1 hour of speech in about 6 machine minutes, where that previous approach took about 33 hours. So we're sort of making this sort of scalable, hence the title. So just really quick, here's an example of what you might find. Given the graphical dot plot method we're using, diagonal lines in the image correspond to repeats. So you see the main diagonal is just from self-similarity, and the off-diagonal line segments, in this particular case, the boxed red one.
For $1 million. For $1 million.
You see that is, in fact, a repeat. And so this is just a similarity matrix frame by frame. Sort of more recent result, and this is going to appear at EMNLP next month, is to take these discovered terms and do standard NLP, IR things using counts of these discovered terms in a given document as opposed to counts of words that you might have in a text document. And so pretty much the result is that you can discover these terms with the algorithm from the previous slide, do topic clustering and classification based on those counts of these automatically discovered terms, where you don't even know where they are, what they are. You just know that they're repeated in the speech, and you know where they occur, and so on. And you can do topic clustering and classification about as well as you can do if you had the manual transcript for the speech. So the idea here is essentially, as the title says, how can you start applying NLP to collections of spoken documents without having an ASR system? Really quick, these is a similarity matrix between given conversation sides from Switchboard. The first 20 are topic 1, the second 20 are topic 2, and you see that you get very high similarity based on these automatically derived terms within topic and not as much.
Guys, we have a problem for a long time. They've been unhappy with our ASR, and now they're finally doing something. We thought we could string them along forever, but
yeah. Well, no. So
look at those last 2 words.
Yeah, I think that was an executive decision by Ken. I think to sort of push that.
As long as it doesn't say without ASR, pizza.
The main idea here, though, at the end of the day, if you have really good ASR, it's going to be about as good on this task, I imagine. The claim here is that you can, if you're in a situation where you don't have the resources to train an ASR system, you can get away without it. Okay, so in conclusion for the main part of the talk, I hope I've convinced you just a little bit, if not completely, that there is something to reducing greatly the sort of representational detail in the speech signal down to these sparse events, and that can in fact be sufficient to recognize speech to a reasonable extent. It's the case that this type of sparse modeling improves automatically robustness to non-stationary noise. With simple adaptation, you can improve robustness to all types of noise. And finally, that there's this whole computational efficiency angle that I think hasn't really been explored yet, but could be significant as well. So that's it.
So can you go back to the beginning? Yeah, that's one of the slides. I have some question. Maybe the first, very, very beginning. Talking about using back all the way back. Back more. No, front. Two more slides up there. 1, 2. One more. Yeah, right here.
Okay.
So for this kind of system, your input really is just the conventional HMI. It's even weaker than HMI. So I actually like your earlier work better. Simply use some representation that HMI is not able to catch.
Yeah. So
like the real time fine scale, because it actually can deal with a lot of problems that HMI couldn't do.
Yeah, so I think you're absolutely right. So I think there's sort of 2 bits. There's how do you go about defining detector sets, and then the second bit is how, once you have a detector set, do you go about modeling words and so on, right?
So you address the later issue in this
and so what I found is that, early on in that work, when you sort of change everything at once, people sort of get a little put off. They're saying, you're changing too much at once. How are we supposed to conclude anything from this? It's not, you're not telling a coherent story. And sort of that combined with just a general sort of desire to actually compete on sort of some real tasks as opposed to, staying restricted to, the toy universe, was sort of the reason why I started just saying, okay, I'm going to fix a whole bunch of stuff compared to the baseline and just start, varying, just looking at this component by component to see if we can show anything a little more sort of believable by mainstream people. And I think
so all the following work is based upon this kind of detector.
Yeah. So everything that happened since there was an original JASA paper that was very long and sort of went into glorious detail about how all of the sort of flexibility that this architecture provides, and then sort of after that paper it was, okay, let's fix as much as we can and do things little by little.
So I mean, thinking about information transmission theorem, right? You get this garbage in, and then you get something to do out.
Yeah, right, yeah.
So it's hard to expect that this one can really do work because what goes in is something that you already know.
It's true, but I think what you can say, this is garbage, and this is derivative of garbage. But the point is I think the argument is that the derivative of garbage.
It's a coding word. Picking up the gold. No. So the keyboard, you miss a lot of things over here. Right? When you go in the end, you still can pick out something nice.
Yeah, well, so the point is this. Yes, exactly. What's the important bits of this guy to keep around? And I mean, that was at the end of the day, sort of the point of this slide, which is what I described to you as this block is not necessarily optimal. I mean, it's just something that we tried. I worked on for a few years. The point is whoever said that this is optimal, everybody just assumes it's optimal because that's what you get taught. And so. The question is this is a worthwhile question, I think, to pursue. That I have the definitive answer is not at all clear. It's just a few years, right? So, yeah.
Any other questions? All right, let's thank the speaker.